I'm Jean-François Gagné. I'm a system engineer at Booking.com. I'm really interested in replication, and this talk will be about MySQL, so Oracle MySQL 5.7 and the new things in 8.0. And I'm really excited about the new things in 8.0 because the preliminary tests that I did are like that. So the low commit rate is the replication throughput on a single threaded slave. And then I alternate 2 minutes of no parallel replication and then 2 minutes of parallel replication. And those are the graphs I'm getting. I'm showing the 4 best graphs of 7. So you'll see the 3 others, but here I have a speed up of 6 times faster, 3 times faster, 4 times faster, and the last one is actually 7 times faster. So I'm very impressed by that, and I will share with you how we end up with those results. For the people in the back, there's still 1 seat there, 2 seats there. Be comfortable. It's better for listening. So those, I'll explain those results at the end of the talk, but this is where we are going today. So quickly, Booking.com, a quick introduction. We sell hotel room on the internet. We're big. There's a lot of people working at Booking. We are actually part of the Priceline group, so even if we are based in Amsterdam, we're owned by a US company, and we have a lot of MySQL server. An interesting thing is only 90% of those slaves are replicating. And the reason for that is in some use case, replication wasn't fast enough for us. So we are actually, so that doesn't mean we have a single copy of that data. We do multi-write from the application. So the application is writing in many MySQL database, but we do not replicate because replication is not able to keep up here. And the usual, we are hiring slide. If you want to join us, come talk to me after. I'll give you my business card and can send me a mail. So what are we going to talk about today? I will introduce parallel replication. I will do a reminder of the ecosystem of parallel replication, what already exists. And then I'll focus on MySQL. So MySQL 5.7 has a new type of parallel replication called logical clock and using intervals. I will talk about how tuning parallel replication in MySQL 5.7, and then I'll introduce what's new in 8.0. So parallel replication is relatively new because it's hard. And the reason why it's hard is because when we run things in parallel on a slave, we need to ensure that data is consistent. If we do a mistake, the data will not be the same on the slave and on the master. So we have data drift, which is really bad. Or we could even have 2 slaves that have different data. If you're reading from one slave, you see something. If you read from the other slave, you see something else. We don't want that. So the challenge of parallel replication is to make sure that the way things are run on the slave leads to the same result that happened on the master. And it's quite important because with single-threaded replication, you can use a single core for writes. It's a waste. We have computers with many cores today. And also, disk subsystems are able to give many read IOs in parallel. RAID 1 is able to give 2 IO in parallel, and SSDs can serve many IOs in parallel. So we want to use that. So I will talk about MySQL 5.7 and 8.0. So MySQL 5.7, in early version, the logical clock parallel replication was based on group commit. This is not true anymore. Now we're using intervals. I will explain what this is. So it's different than MariaDB 10, who is based on group commit. MySQL 8.0 introduced write set. So write set is a way to optimize interval, and it is completely different than what is in MariaDB 10.0, which is optimistic parallel replication. So we got kind of a, like MariaDB is going one way, MySQL is going the other way, and Each has advantages and drawbacks. I will not compare too much those, but if you have questions about those, come to me after the talk. So MySQL 5.7 logical clock. So there's a global variable called slave parallel type that you can set either to logical clock or to database. When it's set to database, which is the default, it is falling back to MySQL 5.6 parallel replication, which is schema based. I will not talk about that more. I already talked about that in the previous talk. So logical clock in the documentation, we can read that transactions that are part of the same binary log group commit on master are applied in parallel on the slave. This is a documentation bug. It doesn't rely on group commit anymore since MySQL 5.7.6. So I reported that recently. It's using intervals. And we will see what interval is in a few slides. Intervals are more complicated than group commit, but they're also more powerful. So it will take a little time to wrap our head around that. To have good parallelism interval, like with MariaDB 10.0, we have to slow down the master to speed up the slave. So we have to tune our workload on the master for it to run correctly on the slave. And we can expect the same problem with MySQL 5.7 as MariaDB 10. So big transaction will slow down parallel replication, and intermediate master will lose parallelism. I already covered those. I will not cover that anymore. So if you want to have more information about that, just look at my slides of the previous talk. By default, MySQL 5.7 will do out-of-order commit. So this is a difference with MariaDB 10 and MariaDB 10.1, which is doing in-order commit. With MariaDB, the content of the binary logs, the order of transaction, is exactly the same on the master and on the slave. It will not be the same with MySQL 5.7. Transaction that can be run in parallel can be reordered. And if you do not want those transactions to be reordered, you can use slave preserve commit order equal 1. But this will only work if you have log slave update, which I report a bug on. Please vote affect me on it if you think it is important to be able to preserve slave commit order without log slave update. Log slave update has a penalty of 5 to 10% in the rate of the throughput of the slave. So I think this limitation should go away. And the fact that it commits out of order has implication on crash safety. So intervals, let's jump into that. It's very complicated on the first introduction. I'll try to simplify that. And to make sure that we understand intervals correctly, we have to understand, well, we can go to understand something simpler before. So MariaDB 10 here, we're not in MySQL 5.7. MariaDB 10 puts some things in the binary log here, which is the group commit ID. And this tells the slave that those transactions here, transaction 185 to 189, are in the same group commit, so they can be run at the same time or in parallel on the slave. We have a transaction alone here, and we have another group commit here of size 7. So before running the next transaction, we have to make sure that everything here is fully committed, fully executed. And if this transaction is long, it will block the slave before, it will wait for this transaction to be fully executed before running the next one. So this is MariaDB 10. So MySQL 5.7 is using two numbers in the bin log. It's using a sequence number. Every transaction has a new sequence number that is increasing. 1, 2, 3, 4. This is very boring. Then it has a last committed. So last committed can be think about on which transaction does that transaction depend. So last committed is the sequence number of the latest transaction on which this transaction depends. So a transaction can depend on many transactions, but on all the transactions that it depends, the one that committed the latest is the one where the sequence number of that dependent transaction will be put in last committed. So let's look at that. So last committed and sequence number is the interval. So here we have a binlog extract with 5 transactions. The first one here has an interval from 6,201 to 6,203. So it means that this transaction here, the transaction 03, is depending on transaction 01. Then we have 3 transactions that happen to commit in parallel, commit together. So this here is kind of a group commit. They all depend on transaction 6203, which is this one. And they have increasing numbers. Then we have the last transaction, which is transaction 6207. 6207 depend on 6205, not 6206, 6205. So it means that those 3 transactions on the slave can be run in parallel. And as early as the second one will commit, this transaction will be able to be started. Actually, what I just said is, for this one to start, everything before that transaction must be committed. So there's a dependency of that transaction on that transaction and everything before. So when this transaction is committed and also this one is committed, the transaction 6207 can start. So 6207 here can be run in parallel with 6206. And this here is the advantage of the interval. We have new opportunity to run things in parallel. But it's also much harder to wrap our head around that. So last committed is a dependency. But how does MySQL 5.7 find this dependency? So on the master, what the master does is every time a transaction is grabbing a lock in InnoDB, it is updating the last committed transaction with the most recently committed transaction. So this is the way the master is tracking dependencies. So here, when transaction 6204 got its last lock, transaction 6203 was committed. And one transaction 6207 got its last lock in InnoDB. Transaction 6206 wasn't committed yet, but transaction 6205 was committed. So we have a last committed here of 6205 and not of 6206.
So that's row lock?
Yes, a row lock. And this is the way MySQL 5.7 gets its parallelism information on the master. And this reaches the slave through the binary log. Yes?
Do you know if there's any plans to support multiple storage engines in a transaction with that scheme?
I have no idea. I have no idea, but it's a very good question. Do we have Oracle engineers here? I can take another question here because it's quite an important concept and I will build on top of that. Yes?
So you said these were row logs, but if they are row logs, then one transaction can depend on multiple transactions?
Yes. So a transaction can depend on multiple transactions, but here we will have a dependency only on one transaction, which is the last transaction that it depends on. So here, the modeling of transaction is simplified to a single transaction and everything before. So there's a simplification here that is done in MySQL 5.7.
You can think of it as a commit log instead of a row log. That can look a commit log.
Okay, so a transaction that is doing an update in InnoDB doesn't have to commit right away. It can sleep and then commit. So this pattern of transaction will generate a very wide interval because it hasn't taken any lock between the last update and the commit. So this is a way why we could have very large interval if transactions are sleeping. So it's not exactly a commit. So this here is not related to to commit on the local transaction, it's related to the lock it's taking. So now that we have those intervals, we have to find a way to tell if it is a good or if it's a bad workload for parallel replication. And again, we'll jump back to MariaDB. With MariaDB, if you have a big group commit size, you can have an int, a clue, an intuition that you will have a good parallel replication speed. And it's quite important to look at that because this is a workload at booking.com. And we can see that the group commit size is size 1. Like this workload here will not run in parallel, not at all. And the reason is because our commit rate is too low. Commit is taking 1 millisecond, and we're not running 1,000 transactions in parallel. So a transaction never commits in parallel. So to be able to have this workload to run well with parallel replication, we have to slow down the master to speed up the slave. And both MariaDB and MySQL introduce tuning for that. So we can tune the workload on the master to add a delay on commit. So with MariaDB, that delay will allow a bigger group. And that delay on MySQL will widen the interval, and it will allow more things to be run in parallel. So here, when I'm tuning MariaDB, I can look at my graph, and I can see now I have a group commit size of between 8 and 10, and so I have a good potential for parallel execution. But with MySQL and with interval, it is really hard to get a sense of a group commit size. It took me a long time to wrap my head around that. And I came up with a metric that we can look at. I called that metric the average modified interval length. Let's forget the modified for now. So it's the average interval length. So if intervals are wide, it means we will have a good parallel execution on slave. If the intervals are tiny, we will have a bad parallel execution. If we want to think in terms of group commit, when we take an average interval length, we can multiply that by 2 and subtract 1, and we get a pseudo group commit size. And this is coming from this group commit here with interval size of 1, 2, and 3. So 1 plus 2 plus 3 to n. The sum is n times n plus 1 divided by 2. The average of that is divided by n, and to get back n, we multiply by 2 and we subtract 1. So from that metric, we can get an idea on how many slaves, how many threads we need on the slave. I cannot tell anything better than that. I know it's a little clunky, but it's the only thing I have. And why do I modify my interval length? So this is a binlog extract. It's coming from production where I've slowed down the master to have bigger intervals. So here I have transaction 93131. That's depending on the transaction. And let's suppose this is executed and this transaction is running. Now I have the next transaction that is blocked. This transaction here is waiting for transaction 31 to execute because we have last committed depending on this one here. But there's something here that we could run in parallel with that. When this finishes, we could run that. So when this is running, we could run that in parallel. But the slave applier is not seeing that. The slave applier is blocked here. And hopefully in a future version that will be improved. But now, this 93124 is actually a 93131 from the point of view of the slave applier. So if I want to know or have an intuition of how things will run in parallel, I need to change that number to this number because of a limitation in the slave applier. I'll let you check that later. This is the script that computes what is needed to get the average modified interval length. And I need to parse the bin log to do that. And if MySQL bin log is failing here for any reason, it's disconnecting from the master, my computation will stop and I will have to do something even more complicated to restart it. I did feature requests to Oracle to expose numbers that would allow, when looking at those numbers, to have an intuition about how things are going. So here, this is for Booking.com master running 5.7. And here I have the untuned metric, very close to 1. And so that means that if I'm trying to run things in parallel here, I will get almost no speed up. And then as I am increasing the value of sync delay, the full name of the variable, I don't remember, but there's a way to tell MySQL, wait a little before committing. And so I'm slowly increasing this value up to 2/10 of a second. This is a lot. I am seeing my metric going up. And so this here, by looking at the metric, you're able to adapt your tuning and to get a sense on the master if this will run fast on the slave. Because before having that metric, the only way we could tune is tune the master and run the slave to see if it's faster. And I'm not satisfied by that. I want to be able, when I do a tuning, to observe a metric and to see what's happening and to have a sense of, will this run faster on the slave? So this is why I did that metric. So now I'm going to talk about 8.0, but I can take one or two questions on that. Yes?
Do you have that set up to publish into metrics by default, or do you just enable this for testing?
Currently, this is a script running in a screen. Eventually, I will put that in our monitoring system when Booking.com will use parallel replication everywhere. But running that as a cron job is not something that I really like because it's MySQL bin log on the master. It's actually adding load on the master. I would prefer to have the metric exposed as status variable by MySQL, and this is the goal of those two feature requests. Again, if you want that to happen, please vote for those on bug.mysql.com. Yes.
So just to confirm that I'm getting this right, in MariaDB, the parallelism is on the group commit order. So it's at the time, basically group commit reflects the time when transaction finishes.
Yes.
And the transaction sequence number is recorded at the time when transaction starts.
No, the sequence number is a commit order. So it's the sequence number.
But how is that different then? I mean, if it's at the time when transaction ends, then how is it different from group commit order, which is also
Okay.
taken at the time when
So
transaction ends?
the sequence number is always increasing. Okay, but last commit here is not the group commit ID, it's the transaction on which it depends. And we can see an example here. Like this is not group commit. This here, that value tells us that this transaction is depending on a transaction that is way before.
So the dependency is recorded at transaction start then?
It's the dependency is recorded as the transaction executes. And yeah, it's
Take it offline because
yes, it's like this here is not simple. Like as the transaction executes, MySQL is keeping track every time it's modifying data, which is the most, which is the latest transaction that is already committed. So it's basically advancing a write view as it do works.
okay. So
So about MySQL 5.7, it's really hard to test if you do not have a MySQL 5.7 master. So I haven't done a lot of tests with MySQL 5.7, but I did more tests in 8.0, and I will explain to you with 8.0 how we can do tests. So MySQL 8.01 introduces the write set. And the write set is a new way to identify parallelism. So in MySQL 5.7, the way last committed is computed is pessimistic. It is computed on the last transaction that was committed. But we have no idea if those transactions are actually dependent. They could have touched different data. So MySQL 8.0 is using something better, and it's putting in last committed the sequence number of the last transaction that updated the same row. So it's much smarter in the way it tracks dependency. And to be able to track those dependencies, MySQL 8.0 introduces the write set. And the write set is a data structure in the master that remembers every row that are modified by every transaction. It's remembering this as a hash, so it doesn't use too much RAM. And this is the write set. And it's quite important to understand that the write set is not something that the slave sees. The write set is a way to generate the intervals. But with the write set, those intervals will be much wider. Instead of going on the last committed transaction, which holds the last lock, it's going to the actual transaction on which the current transaction is dependent. So here we have a much better dependency tracking. So to control the write set, you need to set the global variable transaction write set extraction equal to the hashing algorithm it's using. By default, it's off. And if you want to use write set, you have to use that magical incantation of set global transaction write set equal XX hash 64. What does this mean? I don't know. Just ask the Oracle engineers. And then we have the size of the data structure. The size of the data structure by default is 25,000 rows. I haven't played with that. 25,000 looks quite like a good number. And think about that, remembering 25,000 hashes is quite small in RAM. Like it's in the order of megabytes of RAM. So this is small. It's a very small data structure on the master. And then we have another way. We have a variable that will control how we generate the interval. Commit order is the old way, and we have write set session and write set. With write set, we will actually find the dependency on the row updated. But there's another implicit dependency when you commit transaction, and it's the session. Maybe transaction 1 and transaction 2 that are running in the same session are touching different data. But because they have been run in the same session, there's an implicit dependency between those two transactions. So if you use write set session, you will enforce this dependency to be tracked. So write set session, no two updates from the same session can be reordered or run in parallel on the slave. With write set, we track the exact dependencies, and we can run as many things as possible as long as they're not dependent to each other. But there's a catch here. If you are reusing a connection to write to your master, and if you're using write set session, you will block parallelism identification. So be careful with write set session, because if you have a connection pool, or if you have a proxy that is pooling transaction, it will not work well. So how to use write set on the master? Well, extract write set with the magical incantation and choose if you want to use the full write set or if you want to enforce session dependency. If you're on an intermediate master, and the intermediate master can be single-threaded, you can identify the write set. Of course, you cannot use write set session because it's single-threaded, and then it will enforce session tracking. But if it's single-threaded and you enforce write set, you will actually be able to discover parallelism in your workload with an 8.0 intermediate master and then test with parallel replication and see if things are running faster. This is how I'm doing my tests. I'm using an intermediate master with write set. And if you want to disable write set because you're unhappy, well, just do this. Let's look at the binary logs. So I have a single-threaded intermediate master. In blue, I have no write set. So every transaction is dependent on the previous one. And then with green, I enable write set. So now I have many transactions here that are non-conflicted at all, and now that are depending on the transaction where I start using write set. Here I have a transaction that is dependent on the previous one, and then, oops, I have another transaction that doesn't depend on any of those previous transactions except when I started using write set, but because of the limitation in the replication applier, this here will only be run after this transaction is started. I have more example. So here again, I've enabled write set. It's exactly the continuation of the previous bin log. We can see that the intervals are much wider than before. Yeah, I have interval size of 20. Here, this interval size is 83. It's not very useful because it will block on the previous one, but it's there. And it's there to be used in a future version of MySQL where we will get a better applier. So if we look at my metric now, here I have my single-threaded intermediate master. I enable write set. And now I can see, just looking at my metric, that I have a potential for parallel execution. My metric is between 8 and 20. And obviously, there's something going on in that workload because there's a batch doing something. But now I can see that this write set intermediate master is identifying parallelism. So what's the advantages of write set? Well, we don't need to slow down the master anymore. We don't need to introduce a commit delay for things to commit together and to generate wide interval. It's the write sets that are defining the interval. It will work even at low concurrency on the master. Even if we don't have a lot of parallel session on the master, it will work well. With MariaDB 10, to be able to take advantage of parallel replication, I need tens of connection and sometimes hundreds of connection running transaction in parallel to make sure that things will commit together. Here I don't need that. It allows us to test if it's working even without upgrading the master. And this is very, very good. And it mitigates, if you're using write set, not write set session, losing parallelism with intermediate master. So that's quite good. But it comes with limitations. Only works with row-based replication. Will not work on tables that do not have a primary key or when you update tables with foreign key. So this will probably be optimized in the future. It's the first version, but it's currently a limitation. Each DDL on the master will cause a barrier in write set identification. So I consider that normal, but I did a feature request to be able to count those events on the master, to expose a counter to be able to monitor that and understand if we have bad execution on the slave, understand it's coming from that. There's a barrier at each binary log rotation. So the sequence number is reset to 0 at the beginning of every binary log. I think it's no big deal, but we have to know that. And it doesn't play well with connection recycling. There's actually something in the MySQL protocol called reset connection, but it's not resetting the write set. So I opened a bug about it. Drawbacks. Is it slowing down the master? The throughput, the commit throughput? I don't know. Is it using too much RAM? I don't think so. It should be only in the order of megabyte. But the biggest problem right now is that it's new. We don't fully understand that. And it's the first release, so there are bugs. I know of at least 2 bugs in there. There's one bug in the right set identification. I found that last week. So if you have a delete followed by an insert on the same, on a different row with different PK, but with the same unique key, sometimes it doesn't work well. So if you restart the slave, it works well. But sometimes it tries to run the insert before the delete. And of course, it doesn't work. There's also some deadlock bug, but I'm pretty confident all that will be fixed very soon. So you shouldn't, that shouldn't prevent you from at least testing the technology and see what it is doing for you. On my 7 environments, 6 are working perfectly fine. 1 of them is blocking once in a while here, 3 times out of 5 million transactions. And you just do start slave, it's working fine. And here, I really don't want to sound like a MySQL basher. There were a lot of bugs in MariaDB 2. In MariaDB 10.0, there were many bugs. We found a lot of bugs in MariaDB, even data corruption bug. Most of them are fixed right now. But the technology, MariaDB, is 2 years older, so of course it's more stable. I will skip that. Parallel replication allows to identify new bugs. You can look at this slide later. So write set versus delay. So if we look at my metric again, in green we have the value of the metric with write set. And in blue, we have the value of the metric untuned and tuned. So the blue is actually on a 5.7 master, and the green is on the 8.0 intermediate master with write set. And on the master, at that point, I'm slowing down the master. I'm delaying commit to see the difference. I cannot delay commit for too long on my master. This is production. I don't want to touch that too much. And delaying commit by 0.2 of a second is not something that I want to do for more than 2 minutes. Even 2 minutes, sometimes I could get trouble. Like when I do that, I just put in live at booking, like I'm doing some test. If there's a problem, just grab me, I'll stop. So we can see here 3 environments, so 3 5.7 master. Write set are much better than delaying. There's a third one, there's a fourth one here, and this one is very, very interesting. So write set here is much better than no delay. When I delay the master, I get better parallelism in identification than write set without delaying. But what is very interesting here is when I delay the master, write set is better. So this is very strange. This means that there's still a future for delaying the master. And this is not a one-time thing. I tried it 3 times. So I was messing with production here. I tried it 3 times. And 3 times, when I'm adding a delay, write set is getting better. So my guess here is that adding a delay is actually reordering transactions on the master. Because dependent transactions are blocked on a transaction that is delayed. And this reordering of transactions is getting me a better write set. So I think we have something to dig into here to find like a way to reorder transaction on the master so we get a better write set identification. There was a question there.
So, as I understand, write set will delay though.
Well, with delaying, those transactions will also be serialized because they cannot commit together.
Yeah, but right.
Yeah, I think this. So the question is, if 2 transactions are touching 100 row, but they conflict on a single one, like write set will enforce a hard dependency between 2 transactions, and on the master they might run partially in parallel or something like that. I think they will run partially in parallel. So if the last row that is touched is is the conflicting row is the last row of the transaction. All the bidding will run in parallel. So this is parallelism that is lost. But if it's the first row that they modified, then they will not run in parallel that much. So maybe there's a room for improvement here. But I'm still pretty happy about that. And I think the way Oracle went on simplifying the dependency model to put in the bin log is allowing people to wrap their head around dependencies of transaction. Like creating a dependency graph is hard. Like this is much simpler. So let's talk about speed up right now. So some benchmark result. So I'm using a 5.7 or a 5.6 master with an 8.0 write set enable intermediate master. And I have two slaves, one with SSDs and one with local disk with spinning Rust, so magnetic disks. And I'm running 2 minutes of single threaded with 2 minutes of multi-threaded slave with log slave update, with high durability. I haven't had time to test all the combination of different values of slave, different values of bin log setting, and different durability setting. I haven't tuned the application yet, so this is application from booking.com untuned, maybe with big transactions, I don't know. And this is an untuned MySQL D. So maybe if I'm tuning MySQL D, I will be able to remove a bottleneck. So when you speed up the slave, so in single threaded, the slave is not fast. So there might be a new bottleneck when you speed up replication that you're hitting. I haven't had time to check that. So the way I'm reporting those results, the last number, it's a good thing to see a 0. Here is the number of time I see the bug. So on the 7 test, there's only one environment that has something else than 0 here. 50 is the number of time of iteration that I'm going from 2 minutes single-threaded, 2 minute multi-threaded. I count the number of commits, and then I do a speed up. And I do that 50 times here. Sometimes I do that less, but because I'm doing that often, I can trust my speed up better. Here it's the speed up. A speed up of 1 is the same speed single-threaded or multi-threaded. So here a speed up of 1.6 means 60% faster. Numbers of worker 4. My metric on the interval and the commit rate. This is my worst result. 60% faster on SSDs and 10% faster on disk with 4 workers is my worst result. Here is single-threaded. Here is multi-threaded. Yeah. Here is single-threaded. Here is multi-threaded. Single-threaded, multi-threaded, and so on. So this is the worst result. The next one are much better. So here I have a speed up of almost 6 with SSDs. This is the same graph I showed before. Speed up of 4 with SSDs. Spinning Rust is 2.5. Here speed up of 4 with SSDs. Speed up of 2.5 with disks. Here is the bug. So we can see here that this iteration here hit the slave breaking. So on 10 iteration, I got 3 iteration that broke. So I'm removing those 3 iteration and I'm computing a speed up of 4. So when this bug will be fixed on that environment, I can expect a speed up of 4. And this is where I have a speed up of almost 7. And then the last environment, only a speed up of 80%. But 80% is quite good for an untuned application. So in summary for my speed up, with SSDs, I have 2 interesting speed up. I'm not reaching twice as fast, but I'm reaching 60% faster and 80% faster. 3 very good speed up of 3 to a speed up of 4. Like I'm very happy with that with an untuned application. And I have 2 great speed up. I'm actually very surprised to see a speed up of 7. I wasn't expecting that, but it looks like the Oracle engineer did quite a good job here, and we have a very good speed up here. With disks is different. It's a little smaller. So all that without tuning, and this, I'm not satisfied with those tests. I will do more tests because I would like to try with different workers and different configuration. But that shows quite interesting result as a start. This is 2 weeks old. Yes?
For us that don't remember the MariaDB 10.0 numbers, what ranges were there for speedups there?
Yes.
I don't remember.
Yes. So the speed up with MariaDB were in the range of 4 with optimistic parallel replication. Conservative was worse, so conservative is closer to that. But the result with MariaDB were with spinning disks. It wasn't with SSDs. I am planning to compare with MariaDB 10.1 to do a comparison of write set in 8.0 and MariaDB 10.1 with optimistic parallel replication. I'm planning to compare that eventually, but this is long-term work.
It was roughly 4.
Yes. Mm-hmm. This is a completely different workload. This is different machines, different time of the year. I'm not that comfortable with comparing the numbers. I promised to talk about group replication. This is my only slide about group replication. And what it's saying here is that write set is the data structure used for group replication to identify conflicts. So write set is a technology actually coming from group replication. And group replication is using the write sets to widen the interval so the members of the group are faster than the slaves. So in group replication in 5.7, the group itself replicate thanks to write set. It's widening the interval with the write set. And so the group might not lag when you have slaves lagging. Yes?
Sorry, back to the previous slide.
Yes.
Was that with in-order commits or out-of-order commits?
Out-of-order commit.
Okay. Have you done in-order commits?
Yes, I did in-order commit, but I don't have numbers to show. Okay. But I will when I do more formal and rigorous benchmark. And when I will publish those numbers, I will make you have a number indigestion with all the possible number that we can have here. So write set is actually coming from group replication. So this is the summary of the previous talk. So the first thing is parallel replication is not simple. I was quite happy with MariaDB 10.1 aggressive parallel replication. And with 8.0, I am also very happy with the result. Untuned workload are doing a very good speed up. So what needs to be done next, maybe in the next major version of MySQL, is to have a better replication applier to be able to read ahead and execute more transactions in parallel. MariaDB had slave group commit. I don't know if it's still useful with write set. What is great about write set that it allows anybody on an intermediate master to test parallel replication. That was not possible with 5.7, and it's now possible with write set. So I really encourage you to use an intermediate master, enable write set, and test parallel replication. And optimistic parallel replication versus write set, basically the question you asked. I don't know. I will do test and we'll find out. But as I said at the beginning of the talk, Oracle went the write set way. MariaDB went the optimistic parallel replication way. I'm pretty sure some workload are better on one side than on the other, and vice versa. So which one is better? Like, I think it's the classic IT answer. It depends. So please test by yourself. Share your result. Send me a mail if you have questions. Eric is talking about how we deal with lag on the next talk after lunch. And in the slide that I will publish, there's a few links. Also on the bugs and the feature requests that I opened. You can read here. And please, if it affects you, vote on those so we can have this fixed. Thank you very much, and I have some time for questions. Questions? Yes?
You mentioned that you might want to set the reset session on. So could you give a more practical reason why you want to avoid parallelizing things from the same session?
So it depends on your workload. If you do not want two transactions in the same session to be run in parallel, like transaction, like I don't know, it's your workload. It's if
they are in the same session and do not intersect at all.
So an example where that would be useful is if you are absolutely frightened of exposing on the slave a state that was never exposed on the master. Because on the master, T2 in the same session was never visible before T1. So you could never read T2 before T1. And if on the slave you swap those, or if you run those in parallel, you can now see the result of T2 before T1. So you will expose a read view that never existed. And that might trouble you. So it's slave preserve commit order is also about the same thing. If you force committing in the same order, you know that you will never expose a read view that has never seen before. Because currently on replication, because it's single threaded and it's commit in order, there's kind of promises that are made by the single threaded applier that might not be respected if you swap transactions. And that might break your application. So an example, I don't have an example to give right now.
Whoever is doing that should better put this in a single transaction.
Yes. The bug I found where we do a delete followed by an insert might be a bug in our application. Maybe we should do the delete and the insert in the same transaction. But we actually happen to do the delete and the insert in two transactions. It allows to find bugs. And I think it's a bug in write set. But also doing that in the same transaction would hide that bug. This is the best I can tell you about that.
Thanks.
Other questions? Yes?
It seems like having a way to shadow production traffic would make it a lot easier to test.
Yes. Do you have a product that is doing that?
It's on my mind.
I think it's on everybody's mind. Yes. Being able to shadow production traffic in another server to test new version is clearly interesting. There's a few products out there that do that. PT Query Digest, I think, is doing that using TCP dump. But it's really hard to replay that traffic and expect to have the same result. When you're replaying that traffic, you will have different race conditions in your query, and it will give different results. So it really is a partial way to replay traffic. So if you have more questions, yes?
Yeah, due to MySQL, you mentioned that delay and commit. Is that going to slow down the transaction read on the memory or master database?
Yes. So both MariaDB 10.0 and MySQL 5.7 rely on the commit order on the master and the commit grouping for doing parallel execution on the slave. And if commit is too fast, or if you don't have enough transactions running at the same time, you will never have grouping. So this is where if you want faster replication, you need to make sure transaction will commit together, and you need to delay commit. You do not slow down the transaction, The transaction is running as fast as before. It's commit that is slower, that is delayed to make sure that more transactions enter the same commit window. Yes?
Crash the server or something maybe. If I'm not, I'm thinking that it will be writing to the disk will be a little bit slow.
Well, you're right. Committing to spinning Rust will take 10 milliseconds. But if you have a RAID array with a write cache, it will take 1/10 of a millisecond to commit, or less than 1 millisecond. And if it's taking 1 millisecond to commit, it means you need more than 1,000 commits per second to have at least 2 commits in parallel. That's a lot of transactions. So I need to let people go to lunch, but I'm staying here, and so you can come ask your question. Thank you very much.